Our next bit of review focuses on algebraic vocabulary. We were going to be moving into our algebra unit before spring break, and that involves a lot of higher level language, and so it's good to know the various words that are associated with that so that we're speaking the common language of algebra. We had some notes using a gallery walk that we did on different posters around the room, and some class periods were able to look through this additional practice as well, periods 4 and 6 and 7. So you have this in the notes section of your binder unless you were absent, in which case it would still be great to watch this video. 5th period, we were running a little bit behind before the break, and 2nd and 3rd period, I didn't get to see you the Friday before the break because we're having career day, and many people were on an alpha field trip as well and missed out on the opportunity. This is available on Google Classroom for you to print, and I'll be working off of this copy. If you've already completed this, you're welcome to watch for a review. You're welcome to complete it again, just so it stays fresh in your mind. And if you have nothing but time and you're bored anyway, then you might as well just tune in. One word that we discussed before the break was the word variable, and a lot of people were identifying variables on little entry and exit tickets very well. It would just be a symbol. Usually it is a letter, and it's representing an unknown value. In this case, I see x used as a variable very often. Here there are some n's. Here there's a y. A constant would be a term that has no variable in it. It is just a number standing alone. For example, there are no constants here. They all have x's. 7, though, is a constant. 9 is a constant. There's no variable with it. 10 and 5 are constant numbers. 9 and 3 are constant numbers as well. Several people were confused before the break about the word coefficient. Coefficient is a number that is with a variable. It is a factor. Factors mean multiplication, and when a value touches with another value like this, that means they're being multiplied together. 3 multiplied by whatever the value of x is. You could also read that as 3 x's. So the 3 is the coefficient in that situation. Both of them together make up an entire term. Here the 3 is a coefficient, the 6 is a coefficient, the 2 is a coefficient. If you don't see a coefficient, it's really a 1. It's just 1x. A 4, a 2, that would just have 1x. A 2, an 8, and a 3. I'm going to skip ahead to terms and then go back to like terms. A term is each part of an algebraic expression. These are all algebraic expressions. They do not have equal signs, and they contain algebra, unknown values. And terms are separated by a plus or a minus sign. That's even something that the directions say to do, is identify the number of terms in each of these expressions. So I showed a few students a trick that Mrs. Galan showed me, one of our other math teachers. She boxes hers in, and then wherever she sees a plus and a minus sign, she separates it kind of like you would see a fraction bar. And then you can clearly see 3x is a term, 6x is a term, 2x is a term. This expression has 3 terms. 3x, a 7, and an x. This also has 3 terms. 4n, 2n, and 9. This expression has 4 terms, the x, the 10, the 2x, and the 5. And this expression has 5 terms, the 9, the 2x, the 3, the 8y, the 3x. like terms, I remember it because it's exactly what it sounds like. It's terms that are like each other. They are alike and they have the same variable, or they could have no variable at all. For example, constants are like terms. When you simplify expressions, you combine the like terms together, and that allows you to write a very long expression. For example, 5 terms can be written a lot shorter and simpler if you just combine the like items together. For instance, in the first example, I can combine the x's with one another. 3x's plus 6x's would make 9x's, plus 2 more. This can be simplified to 11x. Again, we don't know the value. We can't solve for what x is, but instead of having something written in 3 terms, we could combine those like terms together and simplify it down to one equivalent term. Here I've got x's and other x's that I can combine. (3x) plus another x would make 4x. I cannot combine the constant with x's because those are not like each other. In the third one, I can combine my n's. 4n plus 2n would make 6n's, and constants are different. But I can still write it simpler from 3 terms down to 2 terms. In the fourth one, I can combine the x's. 1x plus 2 other x's would be 3x's. I can also combine the constants. (10 plus 5 would make 15. In the final one, I can combine the x's together. 2x plus 3x equals 5x. I can combine the constants together. 9 minus 3 would make 6. And then y doesn't have any other like items, so I'll just include that. Just a bit of mathematical etiquette, if you will. Usually when you write expressions, the variables are written first, and they're usually written in alphabetical order. These would be equivalent to each other, but you typically see x's, then y's. If you had them, you'd have z's. If you had a letter or a variable before x, that would be in front. You see them in alphabetical order, and then you see the constants at the end. However, we know that using number properties, that can be applied to algebra also. 6 and 8y can also be written 8y plus 6 because the commutative property says it's fine to rewrite those in any order. That doesn't affect the value. On the back of the item, and mine's separate because I had to print another one at the house, there's a little bit more about expressions and equations and what you can do with them. We were already able to compare and contrast a little bit from their verbal descriptions, how they're slightly similar, a mathematical phrase versus a mathematical sentence. When you see them algebraically, you still see operations and variables and constants and coefficients, and it's just that these have equal signs and the other ones don't. And pictorially, the balance beam represents equivalency, but you don't see that on the expressions. There are other things that you can do with expressions and equations also. For instance, because an equation is a mathematical sentence, it's going to have an equal sign. If you know what an equation is equal to, you are able to do something called solving. Solving is when you find the value that the variable is equal to, and you can do that by working backwards. The ones that we're going to look at, you can use mental math to help you solve because I incorporated some basic math facts into it. When we move forward and we're going to do more formal algebra, you get to a point where you won't know how to do some of them using mental math and you'll need other techniques. So when you see a direction and the direction says solve each equation, solve each equation means find x's value. For instance, 8x equals 16. Think 8 times something equals 16. The x has to equal 2 because 8 times 2 equals 16. In the second, something plus 9 equals 15. The x has to equal 6 because 6 plus 9 equals 15. In the third, 14 divided by something equals 2. X is equal to 7. Because 14 divided by 7 equals 2. In the third, 9x, or 9 times x, because they're touching, 9 is a coefficient, equals 27. X is equal to 3, because 9 times 3 equals 27. 100 plus something equals 136. The x is equal to 36. Because 100 plus 36 would equal 136. For the final one, something minus 19 equals 25. For the classes that completed this with me, a lot of people said that they used inverse operations. Inverse operations are opposite operations. As soon as they saw that the operation was subtraction, they wanted to use addition to help them work backwards, and did 25 plus 19 to arrive at 44. And then once they suspected that the x was equal to 44, they substituted the value back in. And if you do 44 and you subtract 19, you will get 25. So by knowing the value that an equation is equal to, that allows you to go ahead and solve equations. However, with an expression, that's just a mathematical phrase. It does not have an equal sign. And if you don't know what it equals to, you're kind of restricted on what you can do. You can do two things though. You already know that these can be simplified, or they can also be evaluated. First, we'll look at simplifying. When it says to simplify each expression below, simplifying means combine the like terms together, just like we did on the front. So in the first example, I see 3 different terms. They all have x's, which means they're all like terms, and we can combine them together. (3x plus 4x) would equal 7x, plus 5 more. That would simplify to equal 12x. For the second one, we have x's and other x's. 3x plus 13x would simplify to 16x plus 8y's. Notice I'm writing my variables in alphabetical order to follow good algebra etiquette. In the third one, there are x's that can be combined. (2x plus 4x would make 6x, but also there are constant numbers that can be combined. 9 minus 4 is 5. In the final example to simplify, we have a variable of a, (7a plus 3a would simplify to be 10a, and then there are many constant values. 3 plus 9 equals 12, and then subtract 2, that would also equal 10. To be fair, you can also simplify equations. For instance, if your equation were 8x plus 3 plus 4x equals 13 plus 2, you could simplify your like terms that are on the left-hand side. 8x plus 4x would equal 12x. And you could simplify any like terms on the right-hand side. For example, 13 constants plus 2 constants equals 15 constants. So I just simplified everything that was on the left side of the equal sign by combining like terms, and everything that is on the right-hand side by combining like terms, because technically an equation shows equality, but it's built of one expression on the left and another expression on the right. When you evaluate means find the value of an expression, but after you are given a value of a variable. You're going to replace the variable with a given value. For instance, if I only gave you an expression, 5x plus 3, and said, do something with this, you'd say, Ms. Halpern, I can't do anything with that. There are no like terms to combine. I don't know what it's equal to, so I can't work backwards and find the value of x for you. You would need some additional information. But if I tell you that x's value is equal to 3, what you could do is you could take this variable value, you could replace, this is called substituting, you could substitute that into your expression. So if you know that the value is a 3, then we can do 5 times 3, which is 15, and add 3 more. And you could say, well, the value of that expression is 18 if the x were equal to 3. In this expression, assume that the y is equal to a 2. If you substitute that in, 15 times 2 would be 30, plus 18 more is 48. And it may seem like I'm just working from left to right, but I'm still following order of operations because that says solve your multiplication first and your addition last. If the value of x were equal to 9, then you could substitute 9. And then following the order of operations, multiplication, 72, minus 6 is 66. On the last one, if the variable were equal to 10, and 10 were substituted. Multiplication first, 7 times 10 is 70, and if you take away 24, that would equal 46. These would eventually go into the notes section of your binder. It could also help you with your Desmos activity, where you will be comparing and contrasting things about equations and what you can do with them, like solving, things about expressions and what you can do with them, like simplifying and evaluating. It also goes back to the verbal, algebraic, and pictorial representations.